We have 5 minutes, right? Let me put myself on the clock. So I'm proposing.
Zoom in a little bit too. You can if you want.
Yeah. Let me see. I'm proposing projects in all three different directions that we have here. So pure math. You know that I work in graph theory. I think I gave this presentation to the math club, or maybe I didn't, but I can, about graph labelings. And so I'm proposing kind of a, I think, interesting project to look at some kind of basic types of graphs. For example, trees in the kind of simplest versions like paths, stars, caterpillars, lobsters, for example. And then some simple graphs that have cycles. So technically they're not trees, say cycle, book, wheel, or Peterson graphs. And look at different types of labelings that these types of graphs assume. Say, we know graceful labeling, it's one of the most popular and kind of common, but there are a bunch of other interesting labelings like harmonious, magic in many different versions, some labelings and so on. So I have a student, actually undergraduate in Thailand, who recently proved that the star graphs are graceful and found all graceful labelings of a star graph. So that automatically is going to become his master thesis type of direction. So that's something that we kind of strongly encourage our students also to do. So graphs and graphs labelings, if you're interested in pure math. In applied math, I gave a talk maybe 2 years ago about financial mathematics, and I did it again in Europe over my Fulbright. I work with some students there, and it's a very interesting kind of discussion about kind of the discrete world of financial mathematics, and you can always kind of do a comparison with the continuous world. So technically, I'm proposing two different directions here to study. One can be just staying in the direction of financial mathematics, so simple random walk, going to a Brownian motion in a limiting process, and then how these things are used for option pricing. That's the idea of Black-Scholes equations. But we can do just formal mathematical studies, just focusing on something what is called quadratic variation. So you can see here what quadratic variation is. Technically, if you take a function on an interval, say from 0 to t, if the function is smooth in the usual way we think of functions differentiable, then the quadratic variation is 0, and that's very easy to prove. It's not very hard to prove also, but it requires a little bit more deeper understanding what Brownian motion is, that the quadratic variation for a Brownian motion is actually not 0. And it's a fascinating kind of intuition that builds into a mathematician. So it's not hard, but very interesting discussion and can easily go in whatever direction we want to shape it. And another kind of angle that I'm using actually in the applied sense is the study abroad that I recently gave talk in the math club. You know that we have that study abroad in Thailand, math biology study abroad program, where we do different types of water samplings in Thailand, and then we use that data to do different types of research. So there are plenty of opportunities, and I would direct you to my talk that is probably recorded and somewhere in the archives about opportunities to do applied projects while traveling. And finally, another angle that I started working on recently, because I'm on the diversity and the equity committee at SST, and I started kind of studying deeper the ideas of Black mathematicians, female mathematicians, Asian mathematicians, and their contribution in, say, US mathematics. And they're fascinating works. For example, a talk or a kind of research that I would recommend for people who are, say, in math education, and that's something very modern and interesting angle, is to look at works of Black mathematicians. For example, Dudley Woodward paper that is listed right here. And I have the paper and I can show it, but I'm going to run out of my 5 minutes, so I'm not gonna. It's a very interesting kind of direction to study. So if you want to be a researcher that just do kind of type of people and what their research was, or if you want to do more deep mathematical research, so what was the paper and let me understand that mathematical topic, we can veer it again in either direction while touching some kind of a modern and important direction in mathematical study, that is diversity and equity in mathematics. So these are my technically 5 different projects, if you think about it, in any one of the pure, applied, or math way. So welcome anyone who is interested.
Thank you, Dr. Gyurov. That was great.
All right, thank you for letting me have the time. So the preliminary problem is one that we may have seen in classes a long time ago. You got person A and person B are both working, and they can do a job in a certain amount of time. So person A can do the job in 5 hours, person B can do the job in 7 hours. How long will it take for them to complete it together? All sorts of ways of doing this. One of the ways that people think about doing it is by using the work equation that, the work done is the rate at which you do the work times the amount of time it takes you to do it. And so lots of times people form a table where, you put the work, the rate, and the time spent in the table, and then you're trying to figure out how much time does it take for them to work together, right, using this equation. So the crucial thing here, of course, is that the rates add, that if person A and person B are working separately, you can pretend like they morph into one person, and that one person then is working at a rate that is the combined rate of the 2 individual rates, right? And so then you would add that, and then now that you have this rate and this work, you can then find the time spent to find out how much time it takes for them to work together, right? And so then the question becomes, what happens if you start to tweak this and add in breaks, right? So suppose A and B want to have lunch breaks at the same time for 1 hour. How long would it take for them to finish the job? That's not so bad, because if they take the break at the same time, then it is as if you can put that same time anywhere, and then you're just adding an hour onto their combined work times, right? And so, of course, the challenge then becomes what happens if they want to take lunch at different times, right? And so how long would that take? And then all sorts of things come out there. So I've just been thinking about that recently. I think I was helping a student on a problem like this, and I was like, oh, what happens if you just, start doing funky stuff with that? And so I did enough for me to say, oh, this is actually not completely trivial. And I feel like it's accessible. And so that for me rings all the bells that I need, right? Because it's one of these things where it's something that, that is accessible to everybody, but then has enough difficulty in thinking about it that, we can stretch and do lots of difficult things that we don't know the answers to. And so how long would it take if they have different lunch breaks? Does it matter when they have lunch breaks? What happens if they have them back to back versus, and then when is the best time for them to take their breaks, right? So if one is taking a break and the other is working, is it the case that having them have at the same lunchtime is the best time in terms of minimizing the time, or is there some other formulation? And obviously, can we prove that the optimal time for them to have their lunch break is at the same time, if that is the optimal time? And so, of course, we as mathematicians, can go as crazy as we want about it. That was just with 2 people. What happens if we have 3 people, we have N people, and should everyone have their lunch period at the same time? And just in general, when we're talking about breaks, is this the case if you're working over the year and you have this big project, and then now you have some people who want to take their vacation and weeks off? How does this apply to that? And so, again, on the surface, this is an algebra problem with rational functions. But as you may know, and as the people who are listening to this may be hearing for the first time, what's going to happen is that when we start to work on this, new questions will arise. And that's just the beauty of this work in general, is that we just have no idea where it's going to go. So I'm super excited about that. So the plan would be to, work on these simple cases, really get used to what the algebra is doing, only because we know something crazy is going to happen when we start asking harder questions. So it's good to just get used to that. Of course, we're going to try and abstract to new models, add in breaks, find the time with the breaks, and then try and find the optimal time, add more people. And of course, this doesn't have to be in this order. And of course, the plan is in quotes because, you know, when you're working on this type of stuff, new questions arise, and then we'll take complete detours and do something completely different, which is of course all about, which is super exciting. So write up what we have and then hopefully send it out somewhere. I've got some connections for things to be published. This is for everybody on the call at Primus and at Horizons for interesting projects. So, that's like my time. So whatever, this is, again, I'm super interested in problems that have low entry, but can just go anywhere. So that's what really appealed to me about this one. So I appreciate the time.
My talks are all going to be related to graphs. And these are graphs, which are just points and connections to points. And you can think of the points as people, and these are friendships, or you can think of them as computers and their connection between computers or between servers, or any kind of paths between cities, and you travel through them through by airplane or by car. Here's some more interesting graphs, the Peterson graph that Dr. Boyko. It can be a very complicated graph, like this friendship graph of people who are friends with each other. And we can encode graphs into matrices. And once we have them in terms of matrices, and how do we encode them into matrices? Well, for example, this first one here, you see 1 is connected to 2. So in row 1, column 2, we have a 1. And 1 is connected to 6, so row 1, column 6 is a 1, but the other ones are 0, right? And so once we encode them into matrices, well, then we can do stuff with matrices like determinants and things like that. And so that's what I was interested in, and I've been interested in for a few years now. We can break graphs up into its pieces. So right here, from V1 to V2, you see there's an arrow. But you see from V1 to V5, there's no arrow. Well, what does that mean? Well, we can consider that meaning that you can go in both directions as opposed to just one direction. So there it is in both directions. And one of the questions we can ask is, well, how many cycles can we create out of these graphs? And so here are the 3 different ways we can do it. We can make a cycle here and a cycle here. So that's this first one. Or the second one, a cycle on the left, but it can go the other direction. You notice how this is going clockwise, but this one's going counterclockwise. Or you can go through all 5 points by going all the way around. And then we can find out a nice little theorem using this theorem of what the determinant is rather than looking at the matrix. And it kind of, the idea is you're breaking down the graph into constituent pieces. And it's almost like factoring a polynomial, or factoring numbers, like factoring a number into its primes. And that's what we want to investigate, is how to break down graphs and make them into other ones. So for example, here, I try to make a cycle out of, let's say, 4 and 5. But then where does 1 go? Well, I can go 1, 2, but if I go to 3, I can't get back to 1 unless I go through 4, but I already used 4. So I got to say, okay, well, 1 and 2 is its own cycle, but then 3 is by itself. So I can't make any nice, pretty breakdown like I can here. And so that means that my determinant must be 0. Paths are interesting like this. Trees are interesting graphs that have no cycles except for the little internal ones, like between this one and this one, for example, you can make a little cycle. But once you leave, you can never come back. So that's so trees are a fascinating study. And why they're interesting is because if I cut a branch right here, one of these edges anywhere, then I break away, or I separate the dots from one side to the dots on the other side. That has to do with, like, for example, computers and servers. If you have a line cut or a computer server goes down, then you lose communication between one group of servers and the others. Or friendships. If a friendship breaks down, you know, how does the friendships nearby break down? And there's another type of matrix that you can do called a Laplacian matrix that's very similar, except you put in how many edges are coming out of a vertex. So you see at 1, 1, you have 2. But if you look at this one at 1, 1, there's only 1 coming out. But at 2, 2, there's 2 coming out. And what's interesting about this slight variation of the adjacency matrix graph is this wonderful theorem that says that if I take the determinant of the minor of a graph, it's equal to the number of spanning trees of that graph. And again, remember, spanning trees are important because it's all about redundancy and finding out how many ways, you know, what needs to be cut in order to separate them. And it's a way to break down the graph. So my research is interested in taking two maybe well-known graphs and joining them together by a certain number of edges and find out what the resulting algebra looks like. And I ended up with these strange little objects, which are graphs with little like arrows coming out of them. I call them handles because you can kind of grab them like handles. And I came up with this theorem a couple of years ago with Dr. Gyurov. We wrote a paper together that was able to break down these types of graphs into its constituent pieces, kind of almost like factoring them. And so now I'm interested in now zooming in on maybe this area here, just this graph right here, and say, what are the number of trees, or what are the properties of this specific graph in general, or how can I break down these graphs? Or here I have the calculation for a cycle and a complete graph, but can someone write a program for me that can encode this formula, this process, and create for me these graphs using programming instead of just having to do it by hand? That would be an interesting project. And so here are the projects that I have for students. One of them is to break down or factor the graphs and the patterns by writing programs. And you need to know a little bit of linear algebra, some programming, some graph theory. Of course, I'll help you with that. And you can use Mathematica or Python or MATLAB or any kind of programming language, or maybe a combination of them would be the best thing. Another interesting project is to find and analyze the algebraic structure of the determinants of graphs. I'm doing a project or work with Dr. Roberts, and we've been able to find a nice algebraic structure using equivalence class of determinants of graphs. And we were able to find certain monoids and inverses, and that would be your project, is to find a few more identity elements or inverses, or what kind of functions are possible in this structure that we found. And you need a little bit of abstract algebra, some linear algebra and graph theory for this project. And finally, well, no, actually, this one here, a topological data analysis, this takes data, and you can have data and terms, and you can create this, and TDA takes data and takes these points, these scatter plots in space, and creates graphs out of them. And then we can use machine learning to try to analyze the graphs to find different fingerprints or different categories of these data belong. And so you got to know a little bit of programming and maybe some data analysis. And we'll use R or Python to analyze them. And our data files can be from anywhere. They can be from education, from biology, from any kind of interesting field that you might be interesting to. We can apply and we can analyze certain properties of this data using these ideas. So these are the three projects that I'm interested in working on with any student who's interested. And that's the end of mine.
Thumbs up, you guys can see my screen?
Thumbs up.
All right, guys. All right, so I'm Dr. Price, and I'm guessing most of you guys probably have undergraduate research type projects or capstone projects. So you can just share what I'm saying with other people, basically. So let me get back. I'm on the wrong slide here. Here we go. So I wanted to talk a little bit, I guess, how much time do I have, Dan? Do I have 10 minutes, 5 minutes? Give me a number.
5 to 10 minutes. 10
to 10 minutes. Okay,
10
so
minutes. We got plenty of time.
I want to just kind of talk about, what is an undergraduate, research project? What is it like? And so for me, I had an undergraduate research project when I was an undergraduate, and it was just basically an opportunity I felt like to enhance my sort of mathematical experience. So my whole sort of 4 years and 5 years, sort of a capstone. Drawing in things that I learned from other areas of mathematics. Mine was an abstract algebra, and the idea from my perspective is, you simply meet with a professor and you try to formulate a research project. They may have one already formulated for you, or you may have something that you're interested in working on. Maybe you're like, I really liked abstract algebra. I'd like to do something in that. Or I really liked analysis. I'd like to do something in that. And then the idea, you come up with a project with a professor, and you simply, work on that project and attend sort of weekly meetings. So every week you do a little bit of work, you attend a meeting, you review the work you did, you ask some questions to your basically advisor, and you get additional assignments. You talk about what you're going to do for the next week. And basically, you're doing math together. And talked about how I teach a flipped math class, and I found in my undergraduate experience, like I rarely did math with other people. I did math all by myself. It was great fun. I had a great time doing it, right? But it was so much more fun when I could do math with other people. And so that's sort of the idea. Let's have an experience where you can actually do math together. And of course, there is a product. We have to have something at the end to show that we did accomplish something. And so typically you'll have a paper and give a presentation. And so everybody knows kind of what a paper is, and this is a good example of giving a presentation. So you can give a presentation at STaRS, you can give a presentation at Create, or even in our math club, right? And that's the big idea, right? So what is an undergraduate research project? So I like this. There's a lot of discussion about this amongst people. To me, it's very open, okay? So, it could be a mathematical problem, conjecture, theorem, or even a field that you're interested in. It could be more traditional in a sense of, your advisor's research. So, the faculty at GGC has usually some sort of research program going on. So maybe they have some sort of problem in that field. It could be a problem you liked in a math class. Maybe you're fascinated by optimization problems. And so you come in and say, I love those problems. I want to do something with that. And so your faculty advisor can build off that and take those calculus problems and turn them into actually a research project. Or maybe you're interested in some conjecture you've heard, like the Riemann hypothesis, right? So you're like, I'm excited about this Riemann hypothesis. I want to learn more. Well, you come in and you find, ask some faculty member and they can send you to me. And I'm like, I love the Riemann hypothesis. I want to learn about that too. And we learn about the Riemann hypothesis, together. Or maybe there's a favorite theorem you have. Every theorem in mathematics can basically be generalized, and many have been generalized almost to the nth degree. So if you heard of a theorem, we basically can come in and we can find how it's been generalized, research it, find papers on it, and you can give a talk about it and start understanding how that fundamental theorem of arithmetic can be generalized to polynomials and to rings, Noetherian rings, and so on and so forth, right? So all kinds of interesting projects there. Or maybe there's just fields of mathematics that you're interested in, but did not have an opportunity to learn about. Like at GGC, we don't have a class on number theory, right? So I think that's a wonderful field. So if you're fascinated by number theory, come on in and we'll talk about number theory, find some papers or some book or something like that. Like Dr. Pinzon said, we have an STech 2500, which would be perfect for that. Spend a semester on learning an area of mathematics that you're just fascinated by. Or algebraic curves, that's another thing that I'm interested in that, we don't have a class on algebraic geometry, algebraic curves here. Well, maybe you're interested in more of the sort of social science side here, history of mathematics, right? Lifelong passion of mine. So you want to study about different mathematicians or a certain mathematician. Like this semester, a student came to me and said they wanted to learn more about Emmy Noether and the mathematics that she did. And I was like, great. Emmy Noether happens to be a sort of role model to me, right? So I would love to learn more about Emmy Noether and what she did in this case was in physics. Or mathematical periods. Maybe you're interested into the calculus wars between Newton and Leibniz, or you're interested into the history of geometry or the Euclidean, non-Euclidean, geometry, the parallel postulate, whatever, right? So those types of ideas, evolution of mathematical fields. I'm always fascinated by this, or concepts. Take the example of, we just talked about factorization, right? Fundamental theorem of arithmetic. So what can you factor? You can factor numbers, but how much can you factor numbers, right? Can you factor, complex numbers, so on and so forth. And there's all these interesting sort of historical sort of discoveries in mathematics where factorization can always be done. And you guys learn about this probably in abstract algebra, right? Unique factorization domains and so on and so forth. And then math education. I think all the faculty are interested in math education here at GGC. We spend much of our time on this. So if you're interested in just studying like different sort of pedagogies, like Anne mentioned, I teach a flipped class. You know, I'd love to have a student that's like, hey, I want to learn about, you know, the flipped classroom and do like write a paper up on that. For years, I've been wanting to do that, but haven't ever been able to find the time. Or just interested in best practices in the classroom. What are they? Does anybody really know? You know, I mean, you know, so I'm always interested in saying all these best practices. What are they and why aren't we doing them if they are best practices, right? Curriculum design. I think this is fascinating, especially at the collegiate level. Like, do we have the best curriculum? Is it the hottest curriculum in the country, or can we do better, right? Do our GGC math majors get enough computer science? Do they get enough statistics? You know, like, does our program need to be adjusted? I think this would be a great thing for students to work on that are interested in math education as a future career, or interested in applied math, you know, actuarial science. Years ago, I was interested in this. I was thinking about going to become an actuary. And so I have some experience with this, or internships, data science, which you guys have a lot of good stuff here. Which I was like, when I was watching these talks, like, who's teaching these kids Python? I was like, oh, it's Dr. Pinzon down there. Okay, so, you know, or computer science, right? Quantum computing is a field that I've been fascinated by for years. I've had friends in graduate school go into quantum computing. I've always wanted to get into that and learn a little bit more about it. But these are all, you know, good examples of, you know, undergraduate research projects. And basically, you just have to ask, right? So go out, find a faculty member, ask them. If they don't know, come see me. You know, I can direct you in the right direction. There's lots of faculty here that love to work with students. My time is about up, but I do have specific research areas. So, you know, I'm traditionally trained in algebraic geometry and commutative algebra. So my thesis was on the Jacobian conjecture. So if you're interested in conjectures that will last your entire lifetime and you'll never be able to solve, come see me. I'll teach you all about that. I have plenty of experience in that. Actuarial science and data science, like I said, I did take a couple actuarial exams and was interested in internships as a graduate student. So I have some experience working with that, and data science a couple of years ago, I got kind of into that a little bit. So if you're interested in learning more, a little bit more data science, so am I. So come see me. History of mathematics. I belong to History of Mathematics Sigma, and they have this awesome student writing contest. I would love to work with a student and have them write a paper and then submit that to that contest. I think that would be an excellent experience. Like I said, the math education, I teach a flipped class, so I'd love to, you know, write something on that. And then currently, my current research area is graph theory and matroids, and we have a small research group here that meets basically once a week, and we have problems all the time that we don't want to do and want to farm out. It's like, I do not want to write that program. Let's just do something else now, right? But a student could write that program and enjoy that and have a good experience doing that. We're always saying like, oh, we need to, you know, do this, do that on Mathematica so we can explore this idea more. There's various problems there if a student's interested in something that's a little bit more technical or traditional in sense of undergraduate research. Right, that's it, guys. Thanks for listening.
Thank you. Let's thank our speaker.
All right. Hi, everybody. If you don't know me, I'm Dr. Nathanson, and I'm analyst by training. So today I'm going to tell you a little bit about integration, and this is my field. So the title is, this is not your grandma's calculus, and a new improved way to integrate. All of you know what an integral is and what's integration all about. But this integral that you studied in calculus class is just one integral of many kinds. So I'll tell you a little bit about another one, one of the ones that out there. So first we're gonna let's see how I'm gonna. Okay, first we're gonna remember where the integration starts. So integration starts from the area problem. So we want to calculate the area under the curve. So we're given a function f of x. We can start with a positive function. And we're interested in this bounded region, bounded by the curve above, x-axis on the below, and then vertical line that goes through A and B. So the question is, what is this area? And traditionally in calculus classes, we are studying the Riemann integral. And in the Riemann integral, we divide our area into rectangles. We can calculate area of each rectangle by doing just height times width. And then we sum up the areas. So we construct this, what we call Riemann sum. And then we take a limit as n goes to infinity, where n is the number of rectangles. So then more rectangles we have, the better approximation we get. And if this limit is finite, then we have a finite area, and the integral is assigned to be that area. So that's what we typically learn, and this is what Riemann gave us as a definition. There were a few more people before him, which also kind of like part of the history that Dr. Price mentioned. It's interesting by itself, but that's what typically we use. So, and as it turns out that that's good enough and it's widely used, but it's not perfect. There are some kind of deficiencies in this definition. For example, the class of integrable functions includes only bounded and almost continuous functions. And the fundamental theorem of calculus also does not work for all functions that have antiderivative. So this is a formula that we typically use to evaluate the integral. It's integral is a difference of antiderivative evaluated at the end points. But there are certain conditions that we put on these functions that make the class of functions that we integrate smaller than we possibly want. Because everything comes from applications, and we always want to improve the theorems we have. And integration often used to solve differential equations. Many life processes are modeled by differential equations. In real life, there are many good continuous functions, but there are other functions, not so good, that have jumps and some sort of like, if it's like an on-off process, some discontinuities or some spikes. And we want to have a tool that will allow us to deal with this type of functions and maybe some others. So what I'm gonna talk about or kind of tell you is a new integral, another integral that in the literature known by many names. So these are kind of a list of some of them. I was studying this integral by reading papers of Henstock. There are the two main people were Kurzweil, the mathematician from Czech Republic, and Henstock from England. So I was studying Henstock papers and his students. So in my world and in this talk, I refer to it as a Henstock integral. And why is it good? So there are some advantages. First of all, it has a relatively simple definition, as you will see in a second. You don't need to learn like another field or area to understand it. It is more general integral, which means anything that you can integrate with a Riemann integral, you can integrate using this one. It also includes the Lebesgue integrable functions, which is like another class of integral that you study. And the fundamental theorem of calculus also has some improvement that you'll see as well. Okay, so now a little bit get into details here. So how do we define integral? So first we take our interval, so interval A, B typically, and we divide it, we create a partition by this points that we denote by x0, x1, x2, and so on, xn. Then we want to kind of measure the size of this partition, and we introduce the smash, which is like a maximum distance between consecutive points in this partition. In each of the subintervals, we pick up sample point, like the CI in each of the same interval that we call a tag. And then a collection of subintervals with tags we call the tag partition. Now, when we define a Riemann integral, we say that function f is Riemann integrable if the limit of the Riemann sums exist. So this is that same limit of areas of rectangles that we saw before. And if we use a little bit of analysis, we say the following. So there exists a number such that for every epsilon greater than 0, there is a delta greater than 0, so that if the size of the partition, the tag partition, our kind of subdivision that we created with sample points less this number delta, then the Riemann sum is close enough to some number a, so it lies within epsilon distance from a. So if this happens, then the area is given by this number. So it's called the Riemann integral, so this number a, and we denoted the individual sense. So to kind of write it a little bit shorter, this is what we typically write in analysis. So those of you who took analysis class, you probably recognize this formula, this notation. So for any epsilon, there is a delta. So this is our size of this partition. So for any partition you take, if you take any partition of a size lesser than delta, our Riemann sum will be close to this number a. And kind of visually what happened is that we create this partition, and the size of the subintervals can be different, but it's bounded by one constant. So it's uniform across all partitions, all this subintervals has to be less than this number delta. So what happens in the new interval? So new integral. So this is all old school. This is all Riemann integral, what you knew before. We make a small change. Instead of making this delta constant, we make it a function. So now it's a function. It is defined on interval AB and goes from AB to the positive numbers. And when we create a partition, we called it kind of delta, or we kind of small with respect to this gauge function. We selected in such a way that each of these subintervals, so each of these xi minus 1 xi, lies in an interval controlled, an interval around the tag point controlled by the value of the gauge function at that point. So this is Ci tag, so Ci plus delta, Ci minus delta with value of the gauge function at that point. And that's kind of true for each subinterval. So if this is the case, the partition will be delta fine, and that's what will be chosen in our definition. So now in our function is integrable in the new sense, in Hanstock sense, if there exists some number. So we called it a for the first case, now it's h. So that for every epsilon, there is a gauge function. So instead of having a constant delta, now we have a function. So for any delta fine partition, so any subdivision that is small with respect to this delta function, our Riemann sum is close to some number h with respect to that epsilon. So if that happens, then h is a Hanstock integral, and we denote it kind of same way. So as you can see, the definition of this new integral is very similar to the Riemann definition of the Riemann integral. The only difference is that now we measure this kind of how small is partition using a function instead of a constant. And if we take this function to be a constant, we recover the Riemann integral right away. So these non-constant gauges do help us a little bit. So this is kind of an example how we can use it. So if a function doesn't change much, we can take this gauge in such a way that the intervals are taken larger, because the change is small. But if a function changes rapidly, we can create a gauge so the intervals will be smaller. So the partition will be basically taken to reflect the behavior of function. We can also, if the function has some sort of unusual behavior, like function is unbounded or function has some sort of jumps, we can also use a gauge to control those points where some unusual behavior happens. And back to fundamental theorem of calculus. So here's where we get improvement. So this first statement is our regular fundamental theorem of calculus that we learn in calculus for Riemann integral. And the theorem says that if function f has a continuous antiderivative, capital F, and the function f is Riemann integrable, then our formula works. So the integral can be calculated as a difference of antiderivative at the endpoints. So the second statement is a fundamental theorem of calculus for the Hanstock integral. So same starts, our little function f has a continuous C primitive that's the same as antiderivative, which is works for all x, but maybe countable number of points, so we can kind of exclude some points, then little function f is integrable, and the kind of the regular formula also works. What should stand out to you is the following: the integrability of little function f is an assumption in the first case and is a conclusion in the second. So right away, this little tweak that we did in the definition gives us a huge kind of change here. And of course, this is just kind of one theorem, and you know, there are other things that we can do. So this is where I need you to come to me and help me explore more this world. So kind of like possible directions that I just list here, so we can look more in the world of integration and explore the definition and other theorems, compare it more with the Riemann integral, what you know. Every theorem that exists for the Riemann integral can exist or can be improved, or maybe doesn't exist in the world of new integrals. So something to look into. Then we can kind of look at other directions, like what happens in multiple dimensions. Like you know that Riemann integral or integration can be done in 2D, 3D, and n dimensions. So what happens with this integral? How can it be generalized? Anywhere where we have integral, we can try to do a change and see what happens, like transforms, like there is a Fourier transform, there is Laplace transform, other things. I also mentioned Lebesgue integral. So this is another, like a traditionally next step for students in analysis. After the Riemann integration, we study Lebesgue integration and measure theory. Everybody who wants to go to the graduate school, that's a kind of very good way, like an area to explore and be more prepared for the kind of years to come. So, and many more. So if you have interest in rigorous mathematics and anything about analysis and around, come talk to me, and we will find you a topic. Thank you.
All right, let's thank our speaker.
I can't see your faces, and that makes me uncomfortable.
Change your view on the top right.
There it is. Okay, very good. Okay, very good. Hi. Hey. All right. So I was told I have between 5 and 10 minutes, so I'm shooting 7.5 exactly.
On your mark, is that go?
That's what a mathematician should do. All right. Here's my rapid fire research talk. My research covers topology, which, as Brittany mentioned, looks at basically, roughly, classifying shapes that are invariant under continuous functions, and algebra, which is classifying algebraic structures invariant under operation preserving functions. So put them together, you have algebraic topology, which uses topology to study algebra and algebra to study topology. And I have these two pictures that are kind of canonical. We have the coffee cup turning into the donut, and then the blow up cow turning into a ball, which is my new favorite one. All right. Mathematicians love to classify things. We like putting things in little boxes. So like polynomials, we classify them by degree. Functions, we classify them by, are they continuous, differentiable, smooth? Differential equations, are they ordinary or partial, homogeneous, linear? Matrices, we talk about their dimension. Are they invertible or singular? What's their determinant? Things like that. So this is what we do in algebraic topology. We try to classify topological spaces, okay? We have these nice ones, like the sphere, and this one, the donut is called a torus, and the two torus, and the three torus. And one way to classify these is by how many holes they have. That's called the genus. But then we have these really weird ones, right? This one in the bottom left is called the pinch torus. It's like if you take a sphere and you glue the north and south pole together. The one in the middle is called a cross cap, or the real projective plane. This one on the right is called the Klein bottle. And you can't really talk about holes for those guys, right? They're really weird. So we need more tools to classify those. And that's where the algebra kind of comes in. Now, how do we use algebra to study topology? Well, instead of looking at holes, we look at how functions behave. So you can see that line at the top can be continuously moved down to that curvy line at the bottom. And this is what's called a homotopy. And we look at homotopies of loops. So we don't just look at functions, we look at how loops behave on spaces. So here we have a torus, and we look at how a loop going on the outside and a loop going around it, how they kind of behave. And we
gifts are amazing.
Yeah, and we
crazy.
put an algebraic structure on the loops, and that lets us classify topological spaces. But we can also use topology to study algebra. This is what's called the Cayley graph of a certain group. So we're generating a topological structure from an algebraic structure. And here's one that looks kind of weird. This is where we take points and we attach circles to them first, and then more circles, and then we attach two-dimensional spaces on them. And there's a way to do this where you start out with a group, and according to the structure of a group, we attach what it's called cell attaching, and that can tell us something about the structure of the group. It's called the classifying space. This is what I'm particularly interested in. So you can look at it from both directions. Okay, so here are some of the projects that I have in mind. The first one is just algorithms for topological invariance. Can we use Mathematica or GAP or something and algorithmically calculate some of these topological invariants? Aviva is working on some of this right now. Another project is some computer-aided calculations for some high-order group invariants. Now, every math talk should have something that no one but the speaker understands, and so there's my contribution to that, right? No one but me knows what this means. This is what you would be calculating in this project. This is the second homology group of the special linear group over this weird number field with field coefficients. You're not supposed to understand that, okay? This table is something that I've done before. All of these things are vector spaces, right? And I have an upper bound on their dimension, but I want a basis for them, and I don't have that yet. And that's something that someone could help me calculate. This would all be new. So this is the last one, topological data analysis. So Dr. Pinzon has talked about this, and there's been some projects on this. So if you want to work on topological data analysis, I think Dan and I have to duel over which one of us that get to work with you. So just keep that in mind. Again, it uses topology to analyze the shape of data. Okay, so basically this is how my projects work. We have algebra, we have topology, we have some coding, and this is the research projects that all kind of come together right there. And this is the last slide. I do want to show you this website that I have some of the projects listed, and I'll share this with the group. But basically, the first one is calculating spanning sets for that weird equation I showed you. This is use GAP, algebra heavy, topology light. The next one would be some TDA, uses topology to analyze the shape of data sets, mostly topology, some algebra. And this last one I didn't talk about yet, but I did a previous undergraduate research where the student defined something called friendly groups. So the abundancy of a positive integer is the sum of its divisors divided by n, and two integers are friendly, they have the same abundancy. So this student expanded this idea to groups, and she defined friendly groups for a finitely generated abelian. But no one's done it in general. This is only algebra, no topology involved. So this would be a nice project for someone to work on. I'm at 5 minutes and 41 seconds, and so I'm going to officially call myself done.
Let's thank our speaker. That was great. I'm going to have to up my GIF game and my meme game because that was savage. Oh my gosh. Brutal. I want that presentation. You have to send it to me. I'm going to copy all those GIFs.
It's on Google Slides. I'll send you.
Those are beautiful.
I made none of them. I'm just really good at Googling for them.
You made you made the arm wrestling one.
Well, yes, I made the arm wrestling one, yeah.
I say that me, you, and Pragel, we get together and we make our own arm wrestling one right there, right?
That's fantastic. All right, any questions for our speaker? All right, I want to thank all of you for coming and talking with us and hearing these wonderful presentations. We've got them recorded. And so for all of you out there listening to this recorded, thank you so much for watching this. And we strongly, strongly encourage you to contact any professor, not just the ones that you've seen speaking, but contact any professor and see what kind of projects they're interested in, because you never know. You might just be, when a student is interested in something, all of a sudden we professors get excited as well. It's like, okay, well then let's do something, because we love math and we love to do math, but it kind of gets, you know, if a student's not excited about it, then it's not as fun. right? And so we would love to hear you. And you could also talk to other math majors, especially upper level math majors, juniors and seniors, to talk about their experiences in these, and feel free to contact them as well.